Hello everyone and welcome back to another episode of Students Teach Orgo. So today we're going to go over sugars. So I'm going to break up this unit into three separate videos just because of how much content there is. And I think that it's much more digestible in that fashion. So we're going to begin with just generally, what is a sugar? So they're pretty much compounds described by this formula CnH2ON. Not very specific, right? In a way, they are compounds that can have either a keto or a aldehyde group, and pretty much what they could do is they could cyclize. That is my informal definition of a sugar in an orgo kind of way. Um, Almost always we're going to see sugars in the cyclic form, almost always, right? So 99% of the time they will exist in the cyclic form. We will draw them in the Fischer form because integrating them between the Fischer and the cyclic form is extremely useful, and we'll be covering that in this video. All right, so let's continue. So what is a Fischer projection? Well, a Fischer projection is basically a way of drawing a cyclic sugar in a nice linear chain fashion. So there's two types of sugars. We have D sugars and we have L sugars. So what in the world is the difference between the two? Well, pretty much it's when we draw the Fischer projection, if the carbon right before the last carbon, so if we call this the last carbon, right before the last carbon, the one that does not have a stereocenter. So this is the carbon that we care about, the one right before the last carbon. If the hydroxyl group, the OH, is on the right, it's a D sugar. If it's on the left, it's an L sugar. You can do the same thing with amino acids. If you draw the Fischer projection of an amino acid, if it's on the right, it's a D. If it's on the left, it's an L. So it has no relation to RNS. All right, so let's go over the different types of projections we can see here. Starting with the Fischer projection. Okay, so this is the linear form of glucose. As you can see, it's not very easy to go from a linear form to a Fischer projection. Why is that? Well, let's say if you start pairing the different types of bonds, like wedge or dashed, right? So at two, this is wedge, that dashed, right? So if we assume that dashed means like right, as I have here, then wedged should mean left. But we see that's not the case, right? That means that interrelating between these isn't as simple as it looks. No worries there, right? All we need to care about in this course and in general, really, is you look at the Fischer projection, and then you're going to look at the Haworth, and you're going to interrelate between the two. All right, so what do I have here? Well, I have the Fischer projection of D-glucose. Okay, so as you can see, I have four stereocenters, 2, 3, 4, and 5. I always label my most oxidized carbon 1. That's going to be the one with the aldehyde, right? With furanosis, or ketosis really, with ketosis is going to be a little different, but we'll go over that in a bit. Okay, so that's the first step. Label all of these, starting with the most oxidized being 1. You will see that in a 6-membered sugar that has an aldehyde, right, an aldose slash pyranose, you're going to have 4 stereocenters. Now, when this cyclizes, so this is the hydroxyl group. Keep that in mind. This is the hydroxyl group. This is this hydroxyl group right here. This is where the oxygen comes from. It's that hydroxyl group. Going to make that ether quote unquote bond, right? That carbon oxygen carbon bond. All right. But when it attacks that carbon at 1, right? That carbonyl carbon at 1, you can form two types of stereocenters there, right? One where the hydroxyl is on the right, so, or one on the left. That's alpha and beta. And we're going to see that in a Haworth projection even more clear in a minute. But basically, these two newly formed compounds, they're known as anomers. So anomers are a type of epimers. So an epimer is a sugar that differs in stereochemistry at only one carbon. So keep that in mind. Epimer, only one carbon is where the stereochem differs. In this case, this is carbon 1. And these guys are anomers. All right, let's continue. This is what a Haworth projection looks like. Pretty much what we can do is we can show for a cyclic sugar, so this is going to be in this course, a 5 or 6-membered ring, right? You can depict you can go from a Fisher projection into this Haworth projection. And pretty much what it does is it shows the sugar in 3D. However, it is not the actual conformation. It's not meant to accurately convey the ring conformation, but more so the orientation of the groups, right? Of the stereochemical groups. Because when you're doing it in a chair, it's very hard to tell if it's up or down compared to here. Here, it's very clear. So that's the main reason. That's why we use them. All right, so this is just a bunch of vocab. Aldose, you got a sugar with an aldehyde. Ketose, sugar with a ketone. Furanose, 5-membered ring. Cyclohexacetal. Pyranose, 6-membered ring. Cyclohexacetal. All right. This is just some review. So hemiacetal, it's your OR connected to a carbon connected to an OH. And then acetal, it's 2 OR groups connected to a carbon. Okay. All right, let's continue. So here we're going to see some actual depictions of alpha versus beta notation. So if you remember from the previous slide, when we cyclized that Fisher projection, we got both an alpha and a beta sugar. So what does that mean? Well, it means that at carbon 1, you can have 2 orientations. One where the hydroxyl is down, and one where the hydroxyl is up. Okay? So for D sugars only, the alpha means that the OH at C1 is down. Okay? While beta means it's up. All right? So in this case, this is up, up, okay? And even here, up towards you. Here it's down, down, and down. Okay? So we're going to go into more depth, but this is just general for D sugars only. In general, however, this alpha-beta notation really describes the configuration at the anomeric carbon. So for aldoses, this is the carbon that's right here, exactly that carbon 1 where the aldehyde is, right? That's the anomeric carbon, and this carbon right here. And we look at if this hydroxyl is pointing in the same direction, the same face as this hydroxyl on 6. And the same thing here. So if it's the same direction, it's beta. If it's opposite, it's alpha. That's pretty much what you have here. And here we have it, it's opposite alpha, same face, beta. All right? Okay. So how do we get from a Fisher to a Haworth? Well, here I have all the rules. There's a lot of text in this slide. I understand that. Pretty much what you're going to do, first, number all your carbons. So I have them all numbered here. Then draw the Haworth projection, but don't draw the OH groups on these carbons. Pretty much only draw this skeleton here. If I were to draw it alongside with you right now, just draw this skeleton right here. Assume this is a D sugar, okay? That's why we have this group pointing up. If it was an L sugar, it would be pointing down. Okay, next. If you're not told alpha or beta, use a squiggly line like I have down here. That is a terrible squiggly line. Let me redraw that. Better. Okay, so that is going to let you know it could be either alpha or beta, right? It doesn't matter which one because we don't know. And then pretty much from there, you're just going to place all the OHs on your C. So this is 1. So you're 2, 3, and 4. So 2 to 4. You're going to place all your hydroxyls. And you're going to do it up or down. So at 2, we're going to put it down because in the Fisher projection is to the right. So right is down, left is up. 3 is up. So if I were to draw this alongside with you, this would be OH going down. It would be going up, and this would also be going down. So it's not mandatory to draw the hydrogens. Not always necessary. All right, and that's pretty much it. So if I wanted to draw beta here, I would draw this hydroxyl pointing up. If I would draw alpha, it would be pointing down at this anomeric carbon number 1. So hopefully that makes sense. So for furanoses, it's a little trickier, but it's not too bad. Once again, number your carbons starting with most oxidized carbon. Okay, so if we're assuming that this is an aldose, an aldehyde sugar, right? You start number 1, 2, 3, 4, 5 as usual, and then you draw your skeleton, right? Like I said before. So if I were to draw my skeleton, I'm not going to draw the OH groups on carbons 1 to 3. And I assume that this is, I know that this is a D sugar, right? But even if I didn't, you would pretty much, if you knew, you look at your Fisher projection, remember, right before that last stereocenter, if it's the OH is on the right, D sugar, we draw it pointing up. Okay? So we're going to draw our CH2OH pointing up. We're told alpha in this case. All right, so this OH would have to point down. And then we're going to draw carbons 3 to 4. So if this is 2, 3, 4. 4 is already drawn, so 2 to 3. OH going down because it's down here. Down here. So not 3 to 4, but 2 to 3. Apologies on that, okay? So it's a little trickier here, but pretty much you're doing the exact same thing when you're working with an aldose, 5-membered aldose, so furanose. All right. First practice problem. So we're going to convert D-mannose to this Haworth projection shown. So take your time and try this problem out. All right, let's continue. So I'm going to draw this with you. What's the first thing that I said to do? Well, we drew the skeleton. I'm told that this is a D sugar because it says it, but also I look at this OH and it's on the right. So that means that over here, I'm going to draw my CH2OH group pointing up instead of down. Okay, next, what I'm going to do is I'm told that this is alpha, which means that at carbon 1, my OH is down, my H is up. And then from there, I just go left, right, whatever. So this is left, this is left. So left meaning up, make it less confusing, up, down. Okay, up, up, down. Okay, so it's important to understand that this bond right here, between the carbon and the oxygen is this denoted by this hydroxyl here and this carbon 1 because of that attack. Now I know it's not relevant for this particular practice problem in general, but I'm just saying please understand that this hydroxyl to open this up would occur like that. Well, if I were to protonate this, for example. I know it's not relevant to the problem, but this is something I want you guys to keep in mind. Okay, let's continue. So take some time and do this. All right. First things first. What do? Well, we see, is this an L or a D sugar? Well, we're told it's L, but I would look here, and I know it's on the left, so it's L. Great. What does that tell me? Well, that tells me that on carbon number 5, I'm going to draw my CH2OH group pointing down. So this is where it's going to get a little messy. Bear with me here, because I'm using a mouse. So CH2OH pointing down. Then I'm going to look at carbon 1. I'm told to draw beta, which means it has to point in the same direction. The hydroxyl needs to point down, same direction as my CH2OH. Okay, and then the rest is just looking if we draw up or down. So this is up, down, down. So I'm not going to draw the hydrogens on all of them here. So that one is a little hard to get, but hopefully this makes sense. All right, let's keep going. Well, that was actually my answer slide, but oh well. Okay, so practice problem number 3. Convert alpha L idopyranose to the Fisher projection. So this is actually, we're going from the Haworth to the Fisher. So I want you to give this a try. All right. So here's the skeleton that I basically draw. I'm going to draw a straight line going down, and I'm going to draw 4 types of bars, or 4 perpendicular lines. Try to make them evenly spaced. First thing, what do I do? Well, we're told that this is, well, we know this is a pyranose, and we know that this is going to be an aldose. How can we assume that? Well, it's a hemiacetal. That's how we can assume that it's going to be that. So you're going to start with your CHO drawn here and your CH2OH drawn down here. That's the first thing I'm going to do. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. All right, hopefully that makes sense so far. We're told that this is L, which means that on carbon 5 on the Fischer projection, my OH is on the left. And then from there, we just look at 2, 3, and 4, and we see if it's up or down. So 2 is down, 3 is up, 4 is down. So not too bad with pyrenosis, at least. Let's keep going. In this case, I want you to draw we're going from a ketose to the Haworth. So this is a little more tricky. All right, let's review. So how do I do this? Well, first things first, I'm going to have to number. All right, but numbering here is tricky because I need to think about what is making my hemiacetal. What is the hydroxyl that's participating in my hemiacetal formation? Okay? Well, it's going to be once again the same hydroxyl that is participating in the hemiacetal formation in pyrenosis and aldosis, right? It's always going to be the one that determines the D or the L. So this is the attack that I'm doing, pretty much. That OH is going to attack 2, kick up, and cause it to become an OH. Alright? So what does that mean? Well, that means that I am going to label this as my carbon 2, and this as my carbon 5. How did I deduce that? Well, my anomeric carbon, 2, in a ketose is always going to be the one under the carbonyl. I know it's a little hard to think about because usually the anomeric carbon is the one that's right under the aldehyde, but here it's the one on the like one carbon below the aldehyde on our Fischer projection. So when we had our Fischer projection for an aldose, right, if we had this would be the anomeric carbon that we care about. Well, in this case, the anomeric carbon is physically on this carbonyl carbon. So once you have to remind yourself about that, the rest of the problem really falls in place. So we know this is 2, this is carbon 3, this is carbon 4, 5, and then 6 is going to be up or down. So this is D, so 6 we're going to draw up. Okay, draw H here, and then I can go from 2, 3, 4, 5. So we're told this is beta. So let's go back to 2. So remember, beta means that the hydroxyl on the anomeric carbon points in the same direction as that methyl hydroxyl group. So this group right here, it's supposed to point in the same direction as this group. So that means that I have beta here. So OH pointing up. All right. Then at carbon 3, I'm going to draw my H here, OH here, because now I'm just falling up, down. And last but not least, I should have done this earlier, but you could do it at any point. At carbon 2, keep in mind that we have carbon 1 attached as well to carbon 2. We have another methyl OH. So I understand that this might be a little messy. So think about how we did it. First off, you need to recognize that in a ketose, right, the anomeric carbon is the one that's on the carbonyl carbon. It's the same thing. The carbonyl carbon is the anomeric carbon here. That's 2. So we still number from 1 to 6. In this case, we don't number from the most oxidized, but we number just from top to bottom. And 2 is going to be our anomeric carbon, and then 5 once again is going to be the carbon that makes that carbon oxygen carbon participates in that carbon oxygen carbon bond. And then from there, pretty much like always, clockwise numbering around the ring. And then don't forget carbon number 1 and carbon number 6. The alpha beta notation is going to be the same. DL notation is going to be the same. It's just that anomeric carbon is going to change. So keep that in mind. Hopefully that makes sense. All right, let's do some more practice. So convert alpha L idopyranose to the Fischer projection. Okay. What's the first thing I usually do? Well, I'm told it's L. So I'm going to go over here. I'm going to draw my H here, my OH here, because I know it's L. That's the first thing I'm going to do. Next, I'm going to do my aldehyde. And then I'm going to do my methyl hydroxyl group down here. Okay, so this is 6 and this is 1. So this is 2, 3, 4, and 5. Okay, so now at this point, all we really need to do is just look at 2, 3, 4. So 2 is down, so it's going to be on the right. 3 is up, so on the left. 4 is down. There you go. Tried and true method. All right, let's continue. So we're going to pretty much go backwards here. Let's draw the Fischer projection for this furanose. So furanose, in this case, here, how do I know that it's a ketose? Well, I'm going to look at this anomeric carbon. You see that I have this methyl hydroxyl group sticking down? Well, in the previous problem, I had the same thing, right? And I had a ketose. So keep in mind, you will have a ketose here. So I'm going to draw my Fischer projection. Now, think about it, how many perpendicular lines am I going to draw? Think about it. Answer is 3, because it's a furanose. It's a ketose at the same time, okay? So I'm going to draw 1, 2, 3. Okay. Up here, it's going to be my carbon 1. What's my carbon 1? Well, I already have it labeled here. It's going to be the CH2OH. That's carbon 1. Carbon 2, my carbonyl carbon. Carbon 3, 4, and 5 are going to be these carbons of the ring, 3, 4, 5. And then carbon 6 is going to be another methyl hydroxyl. Okay? So far, so good. All right. We see that this methyl hydroxyl group is sticking up. So I know that this is going to be a D sugar. And next, we just fill in 3 and 4. So 3 is up. 4 is down. Hopefully that makes sense. So this is actually D-fructose. So a very common sugar found in fruit. And you just drew it. So I think that's actually pretty cool that we can just draw it on paper like this. And this is something that we eat every single day. Okay. And it hopefully makes sense that it's beta because this hydroxyl right here and then this one, these two are both pointing up the same face. So it's beta. All right, well, that's the end of this video. Thank you so much for watching, and I'll catch you in part 2.